Last time we finished the material on probability and models, and we're now going to move to the topic of computational complexity, scientific programming, growth of functions, different computational architectures. Basically, in a nutshell, in a world where we're processing ever-increasing amounts of data, we need our code to run fairly quickly if we're trying to process a very large data set. So this module number 9, is going to talk about algorithms and running time. So let's begin with an unusual, to some of you a surprising example. Let's look at an array in MATLAB, and we're going to be filling it with values 1, 2, 3, 4, up to 9999 or 10,000 or whatever you'd like. So I'm beginning by, in MATLAB, x equals an empty set. In Python, you could have an empty list, doesn't matter. And 10,000 times, 2,000 times, whatever, I'm going to append the number n to my existing list, and that's it. And I'm going to switch over to MATLAB. So now, let's say that n is 100, and x is the empty set. I'm going to do this in one line. Okay, so for n equals 1 to n, x equals, I'm appending n to x, and I'm ending. And at first I'm showing you that it's instantaneous. You know, I clicked enter, it finished running. And let's see how it's instantaneous it is. In MATLAB, there are different ways how to do that. One way is to use the tick and tock commands, and what's between them gets evaluated. Tick-tock is an informal way of, talking about how the clock is moving forward, and you'll see that this was somewhere between 1 and 2 milliseconds. So that was n equals 100, fairly fast. But now, let's move to n equals 1,000, and it took 6 milliseconds. Okay, still great, no problems. 10,000. A tenth of a second. Now let's think about it. What we're expecting here is that 10,000 times we're adding a number to a list, and we're expecting that, maybe there were a few operations here, like n was incremented. We evaluated whether n, lowercase n, was equal to capital N. We added to the list. So there were multiple operations in the loop, but presumably each of them is super fast. And we'd like to think that, although MATLAB is not a compiled language, we'd like to think that instead of hundreds of millions, possibly billions of operations per second, it can do several million perhaps. And it took a tenth of a second to do, a few tens of thousands of stuff, just stuff or informal. This is already a bit surprising. So let's increase n from 10,000 to 30,000. 7 tenths of a second, starting to be slow. 100,000? So we're expecting several 100,000 operations to happen here, right? And several 100,000 operations, despite MATLAB not being so efficient and so on, we'd expect it to take, some fraction of a second, but it takes 7 seconds. And you can repeat this at home. My laptop is 5 years old, and it's a 3-pound laptop, so it was not optimized for speed. It was optimized for low power consumption, hence a small battery, et cetera, et cetera. So you might get better results, but you're probably going to get something comparable, maybe 3 seconds instead of 7. But the bottom line, we expect this to be very fast. And moreover, if you'll plot the run times, and you'll repeat this experiment many times, and you'll be averaging, and because of the averaging, the noisiness of individual measurements goes away. It's going to be quadratic in capital N, not linear. So what's going on here? So I'm going to now shift back to the module, and we've seen that the code is much slower than we expect, and the question is why. So the reason is that the command where we're appending a number to a list or an array or a matrix, however you want to call it. In different languages, these things have different names. We think that this happens in like a millionth of a second. That's our intuition. You have this computer that ordinarily runs like roughly an order of 1 billion operations per second, and we're just adding a number to a list, no big deal. That's not what's happening. What's happening is that the size of this data structure needs to grow, okay? So the size of data structure X needs to be modified. And what I'm about to say, different programming languages have different styles how to do this, but just let's flow with it here. And so you need to create a new data structure, X prime, temporarily, and we copy the contents of X to X prime, and X prime is larger, okay? And because it's larger, has room for n, the new element. And finally, we erase x. It's no longer in memory. And we rename x prime to be x. So we thought that this line is very quick, but quite a few things happened here. In fact, if you think about it, copying something that has, let's say, 5,000 elements will take something proportional to 5,000 operations. So we thought that the number of operations in my example is linear in 9,999, or to keep it simple, linear in 10,000, a few tens of thousands of operations. But actually, that's not what happened. The number of operations here was something like 1 plus something like 2 plus something like 3 plus something like capital N. Recall in my MATLAB example, N was the 10,000, which later became larger than N,000. And the sum of 1 plus 2 plus and so on, simple arithmetic series, N times N plus 1 divided by 2. It's sort of, not exactly, quadratic in capital N. It's not linear. Now, you might pause now and say, look, whatever your MATLAB implementation is, that's really dumb. Why don't we implement these lists or arrays or whatever they are in a slightly smarter way? And when you ask the software environment to allocate 2001 locations instead of 2000, and suppose that the 2000 it's full, it's not going to immediately give you 2001. It's going to give you somewhat more as a precaution, okay? And let's say it'll give you 2100. So instead of this, what I just described happening 10,000 times, you're going to need to do it for 1, and then for 5, and then for 15, and for... So there are a lot of ways the software environment can support efficiency gains. But I'm saying that if only we had anticipated that we're going to have a data structure of size n, define it initially. So now let's back to the MATLAB. And I'm going to erase all these drawings and so on. All right, so now X is zeros of, I have capital N elements in a column vector and n rows, 1 column. And instead of appending n, X at location n will be equal to n. And recall, this took me 7 seconds, right? 5 milliseconds. That's it. So the code was slow because we made a very silly mistake. If I want to summarize in one sentence, this entire segment of scientific programming material is as follows. I want to teach you the tools to look at hotspots in your code. And if you see that something in your code, from your perspective, should be really fast, and it's much slower than what you expected, I want to give you the tools to identify these problems, look at these hotspots, and again, we're expecting something linear, it's quadratic. So for n equals 100, it wasn't a problem, it was a millisecond or two. But for n equals 10,000, let alone 100,000, we're starting to feel it. So for larger problem sizes, we will catch it. And when we see that it's slower than what we expect, the tools will let you catch the specific segment of code that's slow. And this theoretical understanding that we're going to build over the next week or two is going to allow you to hopefully understand why it's slow and make improvements. So let's back up a bit. In mathematics and computer science, an algorithm is a self-contained step-by-step set of operations to be performed. Algorithms can perform a calculation, data processing, and/or automated reasoning tasks. So in principle, you guys know that I have a parrot. In principle, if I told my parrot how to put together an omelet, if my parrot was well-behaved and obedient, the parrot would know how to put together an omelet. Those of you who have any experience whatsoever with animals will know that when I said obedient and so on, that's not going to happen. So an advantage that computer science people have is that computers are machines, and machines do what we tell them. We boss them around. So algorithms convert inputs into outputs, and there could be different algorithms for the same conversion. So for example, those of you who have studied signal processing, they know that there's the discrete Fourier transform, which is the mathematical way how things are defined, and calculating things that way is slow. Whereas the fast Fourier transform, it's a lot faster, but it implements the same calculation. So there are different ways, different sets of instructions for calculating the same thing, and some of them are better than others. Now, some of them are better than others across the board. Some of them are better than others in different types of resource consumption. So this can get interesting. And also, the same algorithm could be implemented in different ways. And maybe I'm a terrible implementer, and maybe some of you are fantastic implementers and you can do it 7 times faster. But you probably can't do it 7,000 times faster. So as long as my algorithm is pretty good, even if I'm doing it 7 times slower, probably not the end of the world. And that's what we're going to be getting to. Now, when we analyze algorithms, we want to predict the resources that are going to be used or consumed by that algorithm. And there are a lot of different resources that could be used. The running time is what I just emphasized, but memory consumption is often a problem. If, for example, if you have 4 gigabytes in what is in 2020 a slightly less powerful laptop, or maybe on a phone, 2 or 4 gigabytes is reasonable. And if you're processing a lot of data, you can easily run out of memory. So that can also be a concern. Communication requirements. For example, if you're trying to process something on the cloud, you have a ton of computation, a week of computation. And because of that, you're running it on some cluster, and the cluster will accelerate things by throwing 1,000 computers at it, et cetera, et cetera. Communicating it to the cloud may become your bottleneck. If you're implementing things in hardware, the number of logic gates could become your bottleneck. Power consumption on a chip, you're designing a chip, and if it consumes, let's say, 500 watts of power, your circuit may overload. So, or your battery time may go down. So there are a lot of considerations, a lot of resources that could be used. And we're primarily going to look at runtime, but let's be open-minded here. So what sort of analysis we'd like to analyze algorithms, and what sort of computer can we use? So there are a lot of different types of computers, different types of machines. And there are an abacus, or basically using your fingers, which is silly, right? And then there's what I talked about in the module on Kolmogorov complexity, a Turing machine, that it's a hypothetical machine, that it has a tape and it moves it backward and forward and it writes on it and reads to it. Well, that's theoretical. And then you have, at the higher end, you have laptops, desktops, servers, machines with video processing units, clusters with these units, et cetera, et cetera. So different machines in terms of their speed could vary by many orders of magnitude, but we're going to analyze what's called a random access machine model. The instructions are going to be executed one by one, and some of the instructions that you have are that you have memory, you can access it in any location. That's called random access to a random location. You can read and you can write. One read at a time, one write at a time, one instruction at a time, finite number of instructions. So it's an abstraction of a computer, but this abstraction lets us focus on the essence and ignore the small stuff. We're primarily going to focus on the running time, but occasionally I might make comments on the storage and stuff like that. Now, the runtime might depend on the input. It could be that an input of the same size, sometimes the running time will be slow and sometimes it'll be fast. So here's a question. How do we analyze algorithms whose running time varies, depends on the specific input? And there are different answers. One of them is worst case. What's the worst running time imaginable? Another is average case. What's typically happening? And then there's best case. Now, the worst case is often of greatest interest because it provides a guarantee. And in some cases, for some algorithms, the worst case may happen somewhat often. And because of that, we're concerned about the worst case. Moreover, for many algorithms, the worst case and the average case might be similar. On the other hand, there are other algorithms where, imagine that you have an algorithm that the worst case for algorithm number one is okay, and the typical case is the same. You basically always have the worst case, and it's okay. And imagine that you have another algorithm that's, the worst case is bad, but the average case is good. It's not okay, it's good. So how about running the second algorithm with a good average case, and if you see that it's slow, you stop the program, and then you move to the other algorithm whose worst case is always okay. So I'm just saying the design space of possible solutions can be an interesting design space. You don't need a single algorithm. You can have different algorithms with different properties. And finally, how do we measure runtime? We're trying to measure resource consumption. We're primarily talking about runtime, and we're going to be discussing the runtime as a function of the input size. How do we quantify input size? Could it be the number of the items in the input? So for example, if I'm sorting 100 numbers, then the number of numbers that I'm sorting, 100, could be the value of interest. Or it could be that I'm sorting 100 numbers and each of them is represented with 16 bits. 16 bits is typical for a low resolution integer. And then I have 1600 numbers. And sometimes the runtime is proportional to the number of bits that we need to represent the input. Now, in the 16 examples, 1600 versus 100, not that big of a difference. But what if you have like 5,000 different files? And some of these files are 5 bytes long, and other files are a megabyte long. So probably the files that are long, a megabyte or maybe even gigabytes, they take much more runtime than the smaller files. So maybe we need to look at the total. I'm just saying it can be interesting. And maybe we have multiple parameters to characterize the input size. So if you have a matrix, the number of rows and the number of columns could both be parameters of interest. Now, some of you might say, what's the problem? The total number of elements in the matrix is the number of rows multiplied by the number of columns, and just use that. But now suppose that your dependence on the number of rows is a very weak dependence. Let's say square root of the number of rows. So let me annotate. Suppose that you have square root of the number of rows times the number of columns to the power of 3, okay? So what matters here? What matters here is primarily the number of columns. Yes, if you have 100 million rows and you have only 10 columns, yeah, the rows are going to dominate. But typically, assuming that, the number of, you don't have a situation where the number of rows is way larger than the number of columns, typically, for this style of equation, the number of columns becomes important, okay? And all of a sudden, the total number of elements of the matrix is unimportant. We have cubic growth in the number of columns and the number of rows, yeah, okay, we'll deal with it. And finally, how do we measure runtime? We could just count the number of steps executed. And this actually makes sense if we have pseudocode. It's not like formal code in some programming language, but just in words, we write what we're doing line by line. And it's reasonable to assume that this simple computer, we're going to write on every line something that's a simple instruction that it can perform in some constant amount of time, or at least we model it as a constant amount of time. Because of that, counting steps is reasonable. In a random access machine, if we assume that in every line we have one of these core instructions in our instruction set of this hypothetical random access machine, then we're good. Now, what about calling a routine? Calling a routine is one line, but running it, as many of you know, could take seconds, minutes, hours, and beyond. So it's complicated, but we're starting to get a feel for what we want to measure, primarily runtime. And we understand that sometimes we're going to have surprises per that example, and we're going to learn how to reduce these surprises. So that'll be all, and we'll continue next time.